Ladies and gentlemen, welcome back to the live demonstration area. During the next 3 days, we are going to be witnessing live demonstrations of groundbreaking technologies that are shaping the landscape of composite parts manufacturing processes across industries such as aerospace, marine, railway, defense, electronics, and renewable energies, just to name a few. This is the very first time that you can see live revolutionary manufacturing technologies at JEC World, and we wish to thank our partners, Thermwood, Magnum Venus Products, Rock Tool, and Aerovac Composites One for making this experience possible. Now, to dive into this afternoon's presentations, we are very pleased to welcome Thermwood to the spotlight. Thermwood has been the market and technology leader in large format additive manufacturing since 2016, thanks to their innovative large-scale additive manufacturing systems. To present Thermwood's game-changing technology, we are very pleased to welcome Scott VAAL, the LSAM product manager of Thermwood, and Dr. Eduardo BAROCIO, who is the assistant director of additive manufacturing at Purdue University. Gentlemen, the demonstration floor is yours.
Thank you. Well, welcome everybody. My name is Scott VAAL, the LSAM product manager, and with me today is Dr. Eduardo BAROCIO, the Director of Additive Manufacturing at the Composites Manufacturing and Simulation Center at Purdue University, which happens to house a LSAM research laboratory. I'm pleased to have the LSAM 510 additive printer printing live for you today, and it happens to be one of the smallest models LSAM offers. In case it's not already obvious, the LSAM is Thermwood's large-scale additive manufacturing system for thermoplastic polymers. It comes in a broad range of configurations and sizes, up to 15 foot by 40 foot by 5 foot, and with our flagship machines, that length can increase up to 100 feet. LSAMs are available in print-only versions and versions that can print and have a 5-axis CNC router head on the same machine. In fact, some of our models can print and run the router at the exact same time. So of course today we want to talk about large-scale 3D printing, but more specifically about large-scale 3D printing with high-temperature materials suitable for autoclave tooling applications. In fact, that's what we're printing live for you here today. With help from the research team at the LSAM laboratory at Purdue, a full circle demonstration and detailed study was performed on an LSAM autoclave tool. This tool is for a composite air inlet duct. This mock-up tool drew inspiration from the NASA X-59 supersonic experimental aircraft. This study proves that printed composite tooling can be successfully created and used in high-temperature autoclave applications. In fact, the tools and parts used in this study are actually here with us today, and we're also printing another set of tools live for you as we speak. We want to explain the important steps needed to be successful with this process, from how we achieve LSAM quality prints to correctly compensating for anisotropic CTE and other shape changes that happen during the autoclave cycle. And it is also important to understand and compensate for pre-preg material spring, which occurs on the laminate layup material itself during its curing process. I'd also like to mention that this study shows that LSAM printed tools have excellent shape stability after multiple autoclave cycles, showing that longevity can be expected. So with all these factors considered and understood, we can achieve first-time right printed tools that have vacuum integrity directly off the machine and produce dimensionally correct finished parts. So what is required to do this? The key to successfully creating autoclave tooling starts with Thermwood's LSAM, which delivers superior print consistency, provides dynamic control of print temperatures, and has the large-scale focused slicing software needed for large-scale additive. And then we finish this off with the confidence delivered through predictive simulations via the Composites Manufacturing and Simulation Center at Purdue University. So let's explore how the LSAM produces superior print consistency. First, the LSAM is the only machine equipped with Thermwood's patented melt core system for processing materials. The melt core is designed for high output deposition rates to produce large, consistent bead sizes. With our standard melt core producing over 200 pounds an hour and our optional larger core producing over 500 pounds per hour. It uses PID heater control to precisely maintain temperatures up to 450 C. The heart of this melt core system combines a custom industrial extruder, a polymer melt pump system, and a temperature-controlled compression following wheel. This combination produces the most accurate and precise beads, resulting in superior bond between print layers and the best possible solidity between neighboring beads. So let's break down these three key components. First, the melt core's extruder and melt pump work in complete unison to produce the most consistent and precise material output. In large-scale 3D printing, the extruder screw must change RPMs constantly. So this custom patented screw design provides a more consistent melt temperature across these varying speeds. Also, it is known that an extruder alone will not output a consistent material due to extruder surging, especially at high output rates. So our extruder's only job is to keep a fixed displacement polymer melt pump system fed, and then the servo-driven melt pump precisely delivers material to the nozzle. This eliminates the problem of extruder surging and creates the most accurate and consistent beads possible. And another note, it is not necessary to change the extruder screw when changing to different materials. And last but certainly not least, the compression following wheel. An important factor to understand is that unlike other systems, the Thermwood's melt core delivers material to the nozzle, but the patented compression following wheel finishes the bead's final shape and dimension. This provides an all-important active bead compaction. The nozzle tip is actually slightly above the finished bead height, so the nozzle doesn't have to drag through the material or the bead to form the final shape. This prevents excessive material buildup on the nozzle that can be detrimental to the surface quality of your print. This is especially problematic with high-temperature materials. The compression following wheel is actually temperature controlled, but only to prevent polymer affinity. In other words, we don't want the polymer to stick to the wheel. It's actually purposely quite hot while printing. In fact, a study performed by a group at the LSAM Research Laboratory further emphasizes the benefits of this active compaction. Bead compaction aids in the removal of interbead voids. It improves consistency in the printed composite microstructure, which includes repeatable fiber orientation. It enhances interlayer bonding and provides the best results for lateral bead-to-bead solidity. So you cannot achieve quality prints if you can't hold the part securely through the entire print process. And holding parts can be trickier and maybe more important in the large-scale world. LSAM solves this problem with its patented beadboard print substrate. It provides a strong initial tack, and then the heat from the initial beads softens the special layer and allows the layer to float with the part as it cools and shrinks. Then after the initial layers cool down, it holds strong throughout the entire printing process. This prevents distortion and stresses that build in other print substrates. In fact, it actually holds so well that initial machining operations can be done while still attached to the board. And then when ready to release, it can be removed with just a few simple everyday tools. They are reusable and repairable. Let me also mention that the LSAM has a wide variety of print-ready materials ready to use. Using any of these materials is essentially a simple one-click activation to apply all the parameters necessary to print that material. And because of our fixed displacement metering, material configuration files can be confidently shared across all LSAM. It also has automatic routines to load, empty, purge, and clean materials from the system, with on-screen instructions to guide the user through every one of these steps. Now let's explore how the LSAM controls print temperatures. Achieving and maintaining optimal temperature during the printing process is super important. If you print too hot or too cold, you will experience varying problems such as poor bead bonding to excessive part deformation. We must allow enough time for that printed polymer to cool to the ideal temperature before printing the next layer. Layer time control, a patented technology built into the control system, automatically controls the time spent on each layer by adjusting the print speed. This is dynamically handled at the control system. Excuse me. Automatically controlled in real time and ensures the layer is staying at the optimal print temperature. Should conditions change, layer time can be immediately changed dynamically while the machine is still running. So of course, maintaining this optimal temperature results in better, more consistent fusion between print layers. Excuse me. Next, let's explore LSAM's large-scale slicing software. So producing superior prints also requires slicing software to create large-scale programs. Excuse me. So Thermwood developed LSAM Print 3D, which understands all the print characteristics of the LSAM. It also has all the typical features that you would have in your traditional slicing software, plus loaded with unique custom features designed specifically for the large-scale additive world. Excuse me. Also, a notable plus is that LSAM Print 3D slices from real CAD data formats, such as solids, surfaces, and open sheet bodies. Excuse me. I apologize. So there's no need to create a diminished quality STL file just to create a print program. LSAM Print 3D has been used to create well over 100 technical demonstrations for LSAM customers, not to mention our own printing and testing. And there have been countless programs created by our LSAM users. Goodness. This experience has driven the features in LSAM Print 3D and has been continually refined for over 8 years now. I apologize. Oh. Thank you. This has resulted in unique, invaluable patented features targeted for LSAM and large-scale additive. So at this time, I would actually like to pass the baton to Dr. Eduardo BAROCIO to talk about the predictive simulations.
Wonderful.
Thank
you, Scott. Yeah, again, it's a pleasure to be here today and walk you a little bit through the different technologies that we have developed for additive. So a little bit of the LSAM lab established at Purdue. So it was an initiative that happened 3 years ago, basically with the goal of providing research to augment the confidence on the LSAM technology or the large-scale additive technology. So one of the main elements there or expertise that we bring to this technology area is physics-based modeling and simulation. So, and also we have extensive experience characterizing composite materials and also developing simulation frameworks. So our overarching goal at the LSAM laboratory is to enable first-time right printing through a physics-based virtual twin for the additive manufacturing process, where we basically take the machine code that is produced in the LSAM Print 3D slicer to drive a physics-based simulation of the print process, where we can predict temperature history, residual stresses, deformation, interlayer bonding, and not only that, but also investigate the performance of the as-manufactured shape. In other words, we can virtually explore the shape change or the crypta formation that a tool might undergo as it goes through multiple cycles. So just to dive a little bit more into what is behind this technology, so there are two key inputs for this virtual twin called Additive 3D. So one is the machine card and the other one is the material card. Clearly, the machine card captures all the aspects of the process. For example, the effects of flow on the fiber orientation with the printed bead, the interaction of the printed part with the substrate, the interaction of the printed part with the ambient around the printer, and that informs the machine card. So the machine card contains all the material descriptors that we need to describe the material as it goes from the melt state, coming out of the nozzle, and cools down to ambient temperature. So there are multiple physics occurring at multiple scale during the process. So the material machine card inform first the process simulation, where we basically take the machine code that is to drive the physical system, to drive the activation of elements in a finite element simulation while we solve that wide range of physics, including anisotropic heat transfer, anisotropic shrinkage, crystallization, and melting in semicrystalline polymers, and the corresponding shrinkage, the thermoviscoelastic behavior of the material, interlayer bonding, as well as the adhesion with the substrate. Then once we have gone through this simulation of the print process, we can then look at the performance of the as-manufactured shape. In other words, considering all the effects of manufacturing, like residual stresses, local material orientation, we can pose questions like, how does the part is going to perform when it goes in the autoclave? And we are able to predict and compensate for that. So today, we're basically showcasing this example where we exercise Additive 3D and similar technologies to compensate not only for the shape change of the part, but also for the shape change of the composite laminate that is cured in the autoclave at 180 Celsius. So as all of you know, laminated composites always have a spring back when you have curvilinear shapes. So here what we did is first compensated for the spring back of the laminate that is made on the tool. Then that informed the design of the printed tool. Then we predicted and compensated for the shape change of the tool itself. And then we did a fully integrated simulation to verify that at the end, we produced the desired composite part geometry. Just to walk you briefly through one of the examples of a process simulation. So to simulate the print process, as I mentioned, within the machine code, we need a machine card and we need a material card. And we can predict, for example, residual stresses, deformations, temperature history. So you can see here on your left-hand side the evolution of temperature throughout the print process. So it's a highly non-isothermal process. And some of those temperature gradients obviously lead to stresses. And the middle, you can see stresses transverse to the print direction. So, and then on the right-hand side, we're looking at the deformation in the y direction. So similar to traditional laminated composites, this is an anisotropic material. So there are stresses that arise from not only the temperature gradients, but also from the anisotropy of material. And some of those stresses also lead to spring back or spring in this case, as you can see here, for this geometry actually sprung in on the ends. So the geometry that we are printing is compensated to account for that spring in. So as Scott mentioned briefly, so we did a full study on these sets of tools where we basically look at shape and stability, and we did multiple cycles, multiple autoclave cycles, where basically a layup was made on the tool. It was cured in the autoclave at 180 Celsius, and then we laser scan and monitor the shape change over multiple cycles. So you can see on the bottom left corner a deviation plot after multiple cycles, and basically the shape and stability is really consistent throughout the multiple cycles of the tool. So this is the overarching goal of the LSAM laboratory, and we offer access to this type of technology to an industrial consortium that is hosted at Purdue University, through which basically members can get access to Additive 3D to enable first-time dry printing. We also demonstrate the LSAM technology to help basically technology adopters get to that learning curve faster and smarter and avoid costly print trials. And we provide quarterly webinars focused on addressing problems posed by members of the consortium. So those problems a lot of times are really practical problems for which we establish answers grounded on a strong scientific foundation. And last but not least important is all the technical support we provide under the consortium to help you succeed with this technology. And with that, we'll be happy to take any questions that you might have. Please.
Thank you.
Are any of your software packages independent of the printer or printer agnostic and could work with other printer systems?
So the machine and material cards basically take care of that. So the machine cards captures all the features of the printer, and the material cards do the same thing. And those two are basically tightly interconnected. So it's a physics-based, so it's agnostic to even variations in the process or in the practices used with the same machine can lead to different results. So it's agnostic to those things, as long as obviously we capture that. Mm-hmm.
I guess the question I had was more non-Thermwood printers. Would it work for non-Thermwood printers, or is it only specific to Thermwood printers?
So at this stage, we only have machine cards for the Thermwood system. Mm-hmm. Yep.
Any other questions? Any other questions? Okay, I have a question for you. What is the typical, for Scott, what is the typical print bead size on an LSAM?
The typical bead size is 0.83 by 0.2, which would be 21 millimeters by 5 millimeters. It's capable of printing pretty much any bead size, but that is the optimal bead size to retain the heat that's needed to get the good bonding that we need with the system. So.
Mm-hmm.
Okay, thank you. And a question for Eduardo. What kind of experimental validation has been done for Additive 3D?
Yeah, there has been extensive experimental validation we have done at different stages. So, for example, every time we develop a new material or machine card, we do extensive validation of basically through blind predictions of temperature histories, deformation. So we laser scan geometries and compare against our blind predictions. If something doesn't work or doesn't match, we go back and revisit the fidelity of the models and the characterization that was done. So we put a lot of effort into making this a truly predictive tool so that you can use it to engineer and design for additive. Mm-hmm.
Okay, thank you. Another question for Scott. Any other questions from the audience? Yeah? Okay, one more question for Scott then. When you purchase an LSAM, are there other components that will be needed to run the system?
Actually, when you buy the system, it's complete and ready to go. It's production ready. All the accessories needed, such as the dryer, the material delivery system, service, installation, software, training, all of that's included. So drop it in. The only thing you'll need is to purchase material.
Okay. And one last question for Eduardo. What physics are captured in Additive 3D?
Yeah, so there is a wide range of physics, so including anisotropic heat transfer. There is local convection and radiation that depends on the feature of the part. There is, we even capture the heat that is removed with the compactor, either in the form of a roller or a tamper. We capture anisotropic viscoelasticity. We capture shrinkage, anisotropic shrinkage, not only due to the CTE of the material, but also due to the polymer crystallization that occurs in semi-crystalline polymers. We capture polymer crystallization and melting kinetics, so we can predict how the crystallinity is going to evolve throughout the entire print process. And we capture interlayer bonding driven by diffusion.
Okay, fantastic. Thank you so much, gentlemen, for your demonstration. Thermwood will be back again tomorrow at 2 o'clock. And if you would like to ask them further questions on their stand, don't hesitate. They are located at Hall 6P52. And our next demonstration is going to take place here at the live demo zone in 15 minutes with Aerovac. So don't hesitate to come back at 2:45. And if not, enjoy the rest of your day at the JEC World Show. Thank you very much.